Hi everyone, let's talk about the Monty Hall paradox in probability. I'm going to describe a game to you. So what we have is there are three doors, 1, 2, and 3, and behind one of them is a goat. In fact, behind two of them there's a goat, and behind one of them is a new car. And you want to pick the door that has the car. You don't want the goats because they're worth far less than a new car. Now, so the first thing is that one of the doors has a car behind it. In fact, exactly one of the doors. Then what happens is that you choose a door. Let's say you pick this one, but the host of the game doesn't open it. What the host does is that the host picks a different door, so a door different from the one you picked, that has a goat, and the host opens it. So then the question is, okay, so the host opens this one, and you still don't know what's behind this one and what's behind this one. Either one could have a car, and the other one has to have the goat. So the question is, do you switch doors? And basically you have the choice to switch doors at this point after being given the information that this particular door doesn't have a goat or does have a goat. So there is an answer, and the answer is not that the probability is the same either way, because what happens is that most people stick to their doors. Sticking to your original choice is the most popular strategy, and I've tried this with people and they largely stick to their original choice. I'm not going to tell you the answer, but there is an advantage to one of the others. In fact, one of the choices between switching the doors and sticking with your original door has double the probability of making you win than the other. And this has been tried in trials. So people have done randomized trials with a computer, and one of the choices consistently gives you approximately double the uh, number of wins compared to the other. And probabilistically, we'll see that it's exactly double. So here's what we're gonna do. We're gonna first define the problem. So what we essentially have are ordered triples of doors. There R, S, and T, where R equals the door with the car. So what we're going to do is that we're going to label this one A, this one B, and this one C. That'll simplify matters. So R is the door with the car. S is the door you first chose. And T is the door the host opens. And you might think, well, what's the point of this final piece of information? It probably doesn't even give you any extra data. So if it doesn't give you any extra data, if everything just gets dispersed equally according to probability, then there's no harm in keeping it there. But as we'll see, this final piece of information does offer extra information to the player, and that is what will determine whether you should change your original choice or not. Alright, what we're going to do now is draw a tree of possibilities. The tree of possibilities is going to look like this. And actually, before that, what we're trying to do is we're trying to find the probability that R equals to S, which means you should stick to your original choice, and the probability that R does not equal S, which means you should change your choice after the host shows you a door with a goat behind it. So we're going to try to find these two probabilities, and they're going to be complements of each other, but we're going to find them separately. So let's draw a tree of possibilities. So the first one is R, and that's that the door with a car behind it is A, B, or C. The next one is the door that you choose, and again there are three possibilities. It can be A, B, or C, A, B, or C, and A, B, or C. And the final one, it's interesting because if the door with the car behind it is A and the door that you chose is A, then the host has two choices. The host can choose B or C. But if the door with the car behind it is A and you chose B, then the only other door with a goat behind it is C. So there's only one possibility here. Similarly, the only possibility here is B. The only possibility here is C. Here there are two choices again, A and C. Here there is one choice for the host, which is A. There's one choice here, which is B. There are two choices here. One choice, which is A, and two choices here, which are A and B. So let's take a look at when the door that you picked is the same as the door that has the car behind it. So that's this possibility here, and this one, this one, and this one, and this one, and this one. So it looks like there's 6 possibilities for when you should keep your choice the same, 6 possibilities for stay, and 6 possibilities for when you should change your door. So maybe it is 50-50. But a crucial point of probability is that possibility is not necessarily the same as probability. There are very important cases in life when you have to decide according to probability and not possibility. Possibility only equals probability when the probabilities are uniform, and that's not always the case. So let's deal with probability. We have 1/3 probability here, 1/3 here, and 1/3 here. We have 1/3 here again, 1/3, 1/3, 1/3 on this edge, 1/3 on this edge, 1/3 on this edge, 1/3, 1/3, and 1/3. But over here we have half and half. But over here there's only one possibility, so in this branch, so there's only one probability here. Probability of 1 from A, B. If we know that A and B occurred here, then C is the only possibility, so it's probability 1. Similarly, 1 here, half here, 1 here, 1, 1, half, and half. So I'm not going to justify this completely formally, but it involves a chain rule for probability. And what we find is that the probability of R equals to S is equal to, if you look at each of the ones where R equals to S, you find that it's 1/3 times 1/3 times 1/2, and there's 6 of them, so that's equal to 1/3. and the probability that R doesn't equal S, if you look at the 6 chains that lead to that, it's 1/3, each of them are 1/3 times 1/3 times 1, and there's 6 of them as well. So that gives you 2/3. So that means that the chances of you winning if you change your choice is 2/3, and the chances of you winning if you don't change your choice is 1/3. And that means you should change your choice. Thanks for watching, and I'll see you next time.